Sorry, I just got cut off for a second there. I was just trying to show you something really cool, which is that if you have a function that you sort of trivially parameterize, and then you try to use this surface area formula, I want to show you what happens. So the magnitude of r sub u cross r sub v, which shows up right here, right? If you just look at this calculation, look what you're getting, right? When you take the square root of the sums of the squares of the components, it's exactly that formula for the surface area of a function that we saw back in our study of double integrals. Okay? So this reduces down to an earlier formula in that case. What it's really saying is you don't really have to remember this formula if you don't want to anymore. This one covers it all. It covers every possible scenario. And that's kind of nice. So I invite you to play with this formula. You can try out examples such as things that you already know the surface area of, like a sphere. You could try to, you could either do the parameterization of a sphere using phi and theta, right? So you, of course, have phi would be going from 0 to pi, theta would be going from 0 to 2 pi. The full sphere would be these limits of phi and theta, right? And then you'd have to calculate the magnitude of r sub phi cross r sub theta. That's going to be a bit annoying when you look at the parameterization of a sphere and you look at what the partial derivatives are. It's not very clean. So that would take some work, but in theory you should come up with the formula for the surface area of a sphere of radius a. So that would be a good exercise for you to try. You could also, instead of viewing it this way, you could just find the surface area of a hemisphere, and of course that could be done differently, right? Remember, with a hemisphere you actually have a function. You actually have a function, and this would be a perfectly reasonable parameterization of that function. So you could find the surface area of an entire hemisphere and then just double it, because the double of the answer should be 4 pi a squared, which is the surface area of the full sphere. So that's another way to do it, just to get a little bit of practice with this. But again, the main things I want you guys to be practicing are parametrizing surfaces, and then using those parameterizations to find tangent planes to those parametric surfaces, and also the surface area of some portion of that parametric surface as well. So we've talked about the key equations. R sub u cross R sub v is going to play a central role in all of that. And I hope that this makes sense. If there's any questions, by all means, reach out. Feel free to ask me. This stuff is going to get used when we start doing surface integrals, when we start doing Stokes' theorem and the divergence theorem and some of those final applications of the material in multivariable calculus, such as flux, the flux of a vector field through a surface. We're going to need to be able to parameterize those surfaces in order to calculate those flux integrals. So, looking forward to talking to you more about all of that. But for now, I hope that this gives you a good overview of parametric surfaces. Thanks a lot for watching.